I think we're now live. So welcome everyone. In this session, we have Louisa van Zeeland, a senior research engineer at the Allen Institute for AI, and she's presenting a talk demystifying acoustic data for dolphin identification. So just a quick note that to please post your questions in the Q&A box instead of the chat. And Louisa, reminder to start your and over to you.
Cool. Well, thank you for the intro. And hello, welcome back from lunch, and thank you for coming to my talk. My topic is on demystify acoustic data using example of dolphin identification to walk you through how to work on this amazing world of acoustic of sounds. My name is Louisa van Zeeland, and my research interest for the past few years is in studying the three components of soundscapes. So geophysical, which is geophony, ice, wind, tides, seasonal variations, human produce or anthrophony, which is shipping, sonar, piloting, drilling, and so on. And of course, biological or biophony, which is snapping shrimps, fishes, and of course, cetaceans. I am interested in using sounds to monitor the ocean ecosystems as a way to measure progress made in conservation efforts. We also use sounds to study marine mammals, marine animals' behaviors, their migration patterns, their population density, so that we can gain insights through all of this amazing sound as an early indicator that something could be happening in ocean ecosystems. So my goal for this talk is for hopefully they can walk away and start experimenting with acoustic data. So here's a very high level, the content of what we're going to talk about. Since it's right after lunch, there'll be no equations. I won't put you to sleep. I won't put myself to sleep. And let's dive in. So motivations, us humans are very visual beings. We see pictures, we use visual to kind of interact with our world. So why sound, right? Well, sound travel much further than light in the water. Your visibility underwater is very limited. So because of that, many species have evolved to kind of emphasize, focus on using acoustic data over visual communications. And that includes fish, invertebrates, and of course, cetaceans. And many of the cetaceans, like dolphins, and their sound actually can be detected with hundreds to like thousands of kilometers. For example, whales can go to, in this diagram from NOAA, goes to like 50 to 200 kilometers. And so because of that, scientists and a lot of federal agencies actually rely on sound for population monitoring of species to kind of understand where the animals are, what are they doing, and how they're impacted by human noise. And what are some barriers that are stopping us from using these, a lot of data, right? Well, there's a sparsity in open source, very well labeled acoustic data set. So in images, you have the ImageNet, the COCO, but with sound, it's a lot more kind of everywhere, basically. It's less easier to obtain. And then with the sound data, you need expert annotations to get the good data set. There's also additional processing that's often involved that you need to go and make that into a state where you can actually use it for training model. And then, of course, image recognitions and event detections are very different in the sound domain versus in the image domain. So what is acoustic data? Well, acoustic data is pressure waves that is captured by microphone in the air or by hydrophones for underwater. So there are three types of hydrophones that I use for my work. There are anchor hydrophones, which are often used for passive acoustic monitoring. And on the lower left image, you can see a map from NCEI through NOAA of where some of the hydrophones data are, including sense sound. And then the tow hydrophones are usually towed behind boats, and they're usually very noisy. If you have more than one, they can actually do some localizations. And then suction cups, which are like tags, like D-tags that tag onto the mounts of the dolphin's head. And they're really awesome because they allow us to kind of listen into animals in their natural habitats. So while they go and swim around, getting their food, they'll make kind of buzzing noise or raps noise or echolocating to find a way. And then if you have not heard of orca-sound before, I highly recommend you go and check it out. There's a website that shows you where the hydrophones are, and I actually use the data for my data visualization class and kind of map it into kind of like an interactive map to show like where you can find hydrophones, where the sighting view sites are. And if you're connected to Slack channels, they'll send you messages, notifications saying, hey, there's something going on. And Sometimes at night I'll get a notifications, I'll turn it on and listen to the killer whales singing in just our backyard. Well, backyard is in Puget Sound. So pressure waves are continuous, so we need to sample them. And how do we sample them? Well, Nyquist dictate everything. Well, no, he doesn't. But Nyquist is saying that if we want to be able to reconstruct our signals, we want to sample our data at twice the maximum frequencies of our signals. And so in that case, for dolphins, they are usually going from 5 kilohertz to 25 kilohertz. So we kind of round it up to 30 kilohertz, times it by 2. So we sample our data at 60 kilohertz. And when you have the time series sampled in, you come in and you want to chop it into overlapping time segments. And you want to put a window over it so that you reduce the special leakage into out of band. And also when you're truncating time series, you want to give it like a little smoother kind of result when you go through the transformations, the FFT or DFT transformations. So what is FFT, like Fourier transform? You might have seen it as a DFT or discrete Fourier transform or fast Fourier transform. And that is efficient if you're using number of bins that is 2 to the x power. So you often see people use like 128, 512, 1024, 2048 because they're more efficient than using outer numbers. Then you might also have heard of the STFT, the short time Fourier transform, that is very popular also. And but they all produce the same thing. They give you a spectral diagram that is FFT in length, or frequency diagram, and then you have the magnitude of it in the y-axis. So if your sampling frequency is at 60 kilohertz, and then you're using 1024 number of FFT bins, then each of the bin will have about 60 kilohertz times divided by 1024 of the 59 hertz y that is containing the information of the corresponding frequency range of that 59 hertz. And then the magnitude is in the y-axis. Now, if you kind of rotate it, stack them all together, then you got the spectrogram, which is the frequency by time plot. So what are spectrograms? Spectrogram is one of the very common visual representations for when you're using sound data into a form that you can see for us, for human. There are also 3 other representations, MELSPEC, the PCN, and the MFCC, which is mostly for speech recognitions, human voices. So here's an example of spectrogram with very minimal processing, just 1024, and voila, right here. It's a frequency time plot to show where the energy, when I say energy, I mean the sound intensity per frequency time bin. So the color map shows that if it's a lighter color in this color scheme, is higher power, higher energy, and then the darker blue is less signals in there. There is a trade-off between frequency resolutions and time resolutions. And then when you're doing spectrogram, you want to be aware that the frequency and the time are the spatial, it matters. So a lot of times it's good to use hertz per inch or second per inch to keep the spectrogram in the right aspect ratios, especially when you're mixing data. Besides spectrogram, if you change the frequency range into MEL frequency or MEL scale, then you get a MEL spectrogram. It is kind of mapped to what human perceived frequency to what the tone, the actual measured tone, the frequency tone. So it kind of measure up to humans' hearing sensitivity. For example, humans can detect the differences in the lower frequency range much better than the really high frequency range. We just start not hearing as much of a difference. It could be useful for whales that are in the lower range, or music that are in the lower range, but not so much for dolphins' signature whistles, because they're kind of in the high range. So you can see in the spectrogram that the higher frequency, the harmonics are actually being kind of squished together. And then there's another nice way to process your MEL spectrogram. They call it the per channel energy normalizations. So actually kind of preserve the locality, the structure, the harmonics data in the MEL's frequency axes. And the first time I've heard of it was through a blog post to Google AI, and they were using a PCN on triplets loss model to detect humpback whales. So I tried to use that on the dolphin communication, on the dolphin signature whistles. It didn't really go so well, just probably because of the domain, the frequency range are different. And then my colleague tried it with a mobile net V2 and as a binary classifier, and it worked pretty well. So it really depends on the domain or the data that you're working with. But in any case, they are really good for robust detections of noisy acoustic events if you're in the right range. Finally, well, there are a lot more visual representations, but this sort of photo we're talking about today is MFCC, the mel frequency capsule coefficients, and together stack them up, you get the mel frequency substrum. It's basically a short time power spectrums of sound. And in some ways, it's kind of funny because you're doing like a frequency log transform of the mel frequency, and then they just have a kind of nice way of calling it like frequency, and so frequency and spectrum becomes substrum. There's a lot of information on there. It's usually used for human voices analysis, speech detections. So I've never used it for dolphin communications. So here's some example sound libraries and references that you could use. I love using Orgasound. I'm just trying to dive into it a little bit more. So I started my code that I'm going to share with you later using Orgasound data. If you love whales, there's Mobi sound libraries. It's a little harder to parse because of the metadata file that they have and the sample data set. So even though they're from the same data, from the same website, you could have to kind of parse it a little bit. But usually in this kind of work, we spend probably 80% data ingesting and doing plumbings, and then 5% doing model building, right? And then the third one I have here is with Hui, Watkins Marine Mammal Sound Database. And that one, there's a lot of sample that you can kind of click and play, and there's also metadata informations. I have not tried to download them mass in a big chunk at a time, but there probably is a way, but it's a very good reference site to calculate the data. And then Sense Sound, that's the same one. There's a lot of information in there, but they also have a vessel noise information data. They actually have label data too. You kind of stick around for it. That is also from the NCEI with the NOAA website that you can go into. And then Docet, Discovery of Sound in the Sea, that amazing, amazing webinars. Last week, they just had one on physical sounds and how sounds travel in oceans because it's affected by salinity, temperature, and the density, the pressure in the air. So there's a lot of good information in there, a lot of good samples. Whenever I have questions, which is all the time, I just go onto the website and dig around for information. Python libraries, these are some of the libraries I use for analyzing data. Labrosa, I've heard it called Labrosa before, very useful. We can do augmentations with it. Soundfile is my kind of backup that if I can't process something in Labrosa the way I want it, I use Soundfile. SciPy is my go-to tool. I like the control that I get, but that's probably because I'm more familiar with SciPy than Labrosa. And then TensorFlow, they have some called a TFIO, kind of built-in audio library, TFIO the audio, and you can actually do like a real-time spectrogram transformations with the GPU, like as one of the layers. I have not used PyTorch much, but I've heard that Torch Audio is a pretty good library too. So if you use PyTorch, definitely explore that library. And there are many more too. There's PyDub, audio segments, and just kind of dig around and see what you need. So can I augment the data set? Yes, you can. You can definitely augment them, but always work with the domain scientists, domain experts before you start augmenting it however you want it. The common ways are speeding up or slowing down the data, mixing in like the pitch, shifting it up or shifting it down. And you can also mix in different background, but make sure that you do it in the time domain, the audio sequences, rather than doing the spectrogram, because when you shift the spectrogram up or down, you kind of lose that phase information. And so doing the time domain, and be careful how you mix them up too. If you stretch it too much, that dolphin whistle might not be a dolphin whistle anymore, it might be something else. So just work with domain scientists before you start augmenting the data. Can I rotate this? I would say no, please don't. So the upper left corner is a dolphin. The one below it is you flipped it around, or I flipped it the other way for horizontal, and I don't know if dolphins whistle backward. Probably not. If they do, well, we don't know, so don't do it. A dolphin swimming upside down doesn't create a signal that is upside down, so don't flip it up and down either. When in doubt, ask the experts, but yeah, don't flip spectrograms around. So here's the data generators. They've been working hard to create data for us. I got the information from dolphincommunications.org and sarasota-dolphin.org/meet-dolphins. Go check out the website. They have stories about each individual. They're very, very cute. So go ahead and go to the website. I'll play some sound samples for you. And hopefully you can hear them. Here's Joy. And then here's Stormy. It's quite similar. And then here's a babe. And then here's little Alvin's Annie. Her story is really tragic. I gotta turn it up a little bit. She's very quiet. I'll turn up a little bit more and play. All right, so these are the data generators. And just from listening to the sound, it's kind of hard to tell who's who. But if you make it into spectrograms, then you can tell, oh yeah, they're quite different. And I actually randomly picked these four, and I guess two of them actually look kind of similar, but the models are able to detect them quite well. So here's a quick code walkthrough in the last 5 minutes of our time together. Here's my GitHub page, Simple Mind WIDS 2022. If you find any bugs or acquired features, do let me know. If there's some improvements to make, do let me know, work with me. Love to hear feedback and explore algorithms together. So I usually start with the generate config.py file. These stuff I actually started with using it for Parkinson disease audio data set. And then I just kind of fix it up and transfer it to use it for ultrasound. And then a month earlier, the scientists were telling me that I can use it for dolphin communications. And so I switched it and use it for dolphin communications. So it's pretty versatile. You just have to be aware of the parameters. So generate config has all the parameters that I want to use, but there's a caveat in that it could lead to a massive amount of parameters that if you're not careful with grooming them, then they're just dead parameters that we don't use. The main.py is the point of entry for the code base into the acoustic ML package. Those in that package, there will be like data that you can pull data from ultrasound with AWS S3. You do have to go in and look at their bucket and the URL link. I put some comments in there that you can look into. Then there's different data loader for the binary class and then for the Dolphin 4 class that you looked at earlier. And then just other things. Oh, and then the data structures, you want it to be in a wave and then different classes. If it's binary, then you have class 1 and 2. If you have more, then you have more classes. All right, so there are three very important parameters that we want to make sure we use. They're the sampling rate. Remember, it has to be Nyquist sampling theorem, twice the frequency of your target, which is for dolphins is we expect it to be up to 30,000 kilohertz. 30 kilohertz. So we use 60 here. NFFT, I use 1024, and the window I use Hamming. But Hamming will work. Kaiser might work. I've seen a lot of in the ocean domain they use Hamming or Hamming. So those are the three parameters that are like very important. So sampling rate, NFFT, the number of frequency bins, and the windows. The other stuff, you can kind of play with it, thresholding, dynamic range, and all that. Loading audio files, the two main libraries I use are Labrosa and Soundfile. So Soundfile is the SF here. I use it for FLAC because Labrosa doesn't have the higher sampling rates that I would want sometimes for the FLAC files. So I switch to a Soundfile. Sometimes there are more than one channel, so you want to average them. And then with Wave, I just use Labrosa with the meta files. I usually give an offset, and then I have the durations of the time that I want. Creating a spectrogram, I like to use SciPy because it gives me back frequency and time, so I can kind of mess around with it and play with it, pattern, whatnot. Labrosa, I'm sure they have the feature. I'm just not as familiar with the library, so I use it less. But they both will produce similar spectrum. And here's an example. So the ones on the upper left corner is using Labrosa, and the one on the lower right corner, no, still lower left corner is using SciPy. So if you can tell it's kind of similar, very little differences. And if I were to make sure all the parameters are the same, they would probably look a lot more similar. So here's the sound that I'll play for you. So it's pretty low frequency right now, like our dolphins earlier. So this is where mel frequency spectrogram can come in pretty handy. You can tell that there's a lot more details, more information that I can look into compared to just doing a spectrogram, just because of the scale on the y-axis is kind of following the perceived human range. So we get to see it more. There's an article saying that mouse spec is actually MFCC is biased because the way it's being created. But anyway, people do use them. What is this? Finally, the build model. So with the Dolphin dataset, it's hand created, it's super, super clean. So all we really need at the time was just a base model built in from TensorFlow. I added a few more fluff and different layers to it, like using ImageNet to help train the model a little quicker. A couple of years ago when I looked, ImageNet does not have spectrogram, so make sure if you use that, freeze the, when you freeze a layer, freeze some of the layers, not many of the layers, so that the model can actually learn from it. It does help with training the model a lot quicker because I'm using my laptop and I don't have GPUs when I train the sample data set here. A very basic two-layer CNN, it performed pretty much just equal as well as the mobile nets. Again, the data is really clean. It also worked decently well. Actually, I found it a little better with the Arkansas data, just because the deep network is harder to tune, I think. So here's the confusion. Kind of help decide, like not decide, but to see the performance of different models. I did lower the patients a little bit, smaller patients, like waiting time for the two-layer CNN, just because it was following the training curve so closely, or just it was still getting perfect result, and that's kind of boring. But anyway, probably not fair comparison, but both did really, really well for the small amount of data set that we have. I think I have about 200 examples each, and that is split into validation and test sets. Anyway, we're at time, and welcome any questions that you have. And if you have questions and I can't answer, email me at substrom@gmail.com. And if you put a little tag on WI ideas, and I know to look for them or filter them so I won't miss them. And it was getting a perfect result. That was point. Yes, yeah. I mean, you want challenging problems, right? But it's good, right? Either way. Either is good. Good for a scientist. The model is good, and good that as well. Challenging problem is fun. Anyway, so I think I'm supposed to click on some buttons on the Q&A, and let me know if I'm doing this wrong. Okay, so one of the questions is, where do dolphins that we just heard live? Oh, they're in Sarasota. They're in Florida. I don't have a map. I should put a map in there. But in Sarasota, Florida, go check out their website called dolphincommunications.org, and or Sarasota Dolphin, and then / or just a website. It's really cool. It has all kinds of information about the dolphins and individuals and samples, and the scientists actually mentioned about they would love to open a data set that we've been training with, so that people can use as a benchmark and learn more about the data. So if it's open, I'll update it into my GitHub page, or GitHub page. Is there a variability in dolphin voices greater or less than defining human voices? Oh, I don't know much about human voices, even though my email account sounds like I should. I would say human voices are kind of in the smaller range. I don't know if that's kind of help with the questions, but in that they're smaller range, I think it's really rare to have more than 2,000 hertz. I don't know if, and someone in the audience, if you know, please help answer this. But dolphins, they go from 5 kilohertz all the way to 25 kilohertz, or maybe a little bit more, plus or minus. So they do kind of vary a little bit, vary quite a bit. They're modulating frequencies. And from my understanding is that just a 1% of change in frequency, let's say the mother and caps pair, the caps will try to follow the mother. So there's like a little Fourier at the end that could totally change who the individual is. So they're very sensitive. And then one question is identification of individuals the main test you use this for? For them, yes. So when we were trying to look into what are the pain points so that we can use machine learning to help with the workflow, it turns out that to detect sound is pretty easy. We do have a detector. Gracie, that you hear from her in 2 talks after this, is that she did the detector side of the dolphin signals. But that part is actually a lot cheaper because they can hire grad students or even college student, pay them minimum wage and have them like identify all the segments, right? I'm just kidding. But you can do that like crowdsourcing. But to actually identify individuals, it requires experts, annotators, that people have been working in this field for quite a few years. Even then, they have like, a few people in line to kind of double check everybody's work. So that would cost a lot more money. It takes a lot of effort, and so that was the pain point for them. So that's where machine learning could come in and help. The other tests, such as identifying which dolphins are doing, it's kind of, yeah, there is actually. So with the DTAG, our scientist Franz, he's using different like rasping, buzzing, echolocating to determine what the dolphins are. Like when they're hunting for food, they might do some kind of buzzing sound, or they're looking for locations or finding the fronts. Well, finding fronts, they use other whistles, but when they're locating themselves, they use echolocation. So their sound would really help kind of tell us what they are doing. And then he's really into studying dolphins' behavior. So he used different sounds and at what event and what time that they do things together. So dolphins are very communicative, very kind of friendly animals, so they talk to each other all the time. I think that's, I don't know. Kristen, I'm just in the vein of decomposition for sound. Yes, there is also a wavelet. Wavelet information can be used to create spectrograms in Fourier. I don't know about creating spectrograms, but wavelet decomposition is a very, there's a lot of paper actually in there. We use the spectrogram mostly because, well, it's easier, we want to work with scientists so that they can actually see things like kind of build trust, and they use spectrograms. So it's easier to work with them and show them, oh, here's what we're doing, the data we're processing. And then, whereas wavelet decompositions, I'm not really sure. I can look into and get back with you too if you email me. I do have a book on wavelets. I spent a whole quarter on it. So I should be able to answer this, but I couldn't. I'm sorry. Hey, Kristen.
Okay, hello. I think that's probably all the questions we have time for. So thank you for the great presentation, Louisa. It was fun. It was fun to hear the dolphin sounds and see the images.
They're so cute.
Yeah. So if you have additional questions, you can send a direct message to Louisa in Excellements or email her. I just posted her email in the chat. And so we'll look forward to seeing you in following sessions and the expo booths. So thank you.